fifth period you had an unusually difficult combustion problem because of this strange chemical formula here, or chemical name, but this does give us a lot of opportunity. Even though it's pretty weird, it does give us a lot of opportunity to practice some skills. So we're going to look first of all at the skill of drawing out the structure. Hex means we've got 6 carbons, so I'm just going to put out 6. Cyclo means that it's in a circle, so I'm going to put my 6 carbons in a circle. I'm going to leave myself plenty of room so I don't have to be scrunched up. Now the fact that it has the Y and E into it means that there's a triple bond somewhere. Now we do not have a number in front of this saying like 1, 2, 4 diene or triene. So what that means is we have 1 triple bond, and that 1 is understood to be the first carbon. And since this is a cyclic structure, we can pick any of them to be our first carbon. So we'll just pick this one, and this will have a triple bond. So I can connect my other carbons. Now I'm going to number my carbons. I come over here to where it says 3-ethyl. On my third carbon, I'm going to have an ethyl group, which is a CH2CH3. Now, this says dimethyl, so that means I have 2 methyl groups. Both of them are on my 4th carbon. Okay, so 2 methyl groups on that 4th carbon. At this point, I'm not finished yet because I have to add in my hydrogens. Remember, each carbon has 4 bonds. So if I look here, I've got 1, 2, 3, 4 bonds around that carbon. No more hydrogens can be added. 1, 2, 3, 4 bonds around that carbon. Can't put any more hydrogens there. This one, this carbon has 3 bonds, so I can put a hydrogen right here. This carbon has 1, 2, 3, 4 bonds, no hydrogen there. This one has 2 bonds, so I'm going to put a hydrogen and a hydrogen so that I have 1, 2, 3, 4 bonds. Same thing for this one. 2 bonds, 3, 4 bonds, so that gives me hydrogens. So the cyclo is the circular form. The hex means that the parent chain has 6 carbons. The ine means that we've got a triple bond. The 3-ethyl means that we've got an ethyl group on the 3rd carbon. Dimethyl means we have 2 methyls. Both of them are on the 4th carbon. Now the next thing we have to do in order to do this problem is we have to set up our combustion equation. And in order to do that, I need to know the molecular formula. So the molecular formula, I have to just count everything up, and this is where getting all the correct number of carbons will make a big difference. Okay, so I'm going to use another color here to help me out. So I know that my molecular formula is going to have carbons and hydrogens. So I've got these 6 carbons, 1, 2, 3, 4, 5, 6. I have 7, 8, 9, 10 carbons. Now with hydrogens, I'm going to do the same thing. I've got 3 and 2 is 5, that's 6. 6 and 3 is 9, and 3 is 12, 13, 14, 15, 16 hydrogens. So the molecular formula for this monstrosity is C10H16. So again, step 1 was to draw my structure. Step 2 was to find my molecular formula. Step 3 is to put this into a combustion equation. So remember, any I'm going to leave myself some room here. C10H16, any fuel at all, is going to need oxygen, and it is, assuming complete combustion, going to give us carbon dioxide and water vapor. Now, at this point, I need to balance my formula. Balance my equation. Remember, start with your carbons, then do your hydrogens. I've got 10 carbons here, so I'm going to do this with pencil, so if I have to change numbers, it'll be easy. I'm going to try to put a 10 there. I've got 16 hydrogens, so let me put an 8 here, so 8 times 2 is 16. Now, remember I did carbons first, hydrogens second. Next I'm going to do my oxygens. On this side, I've got 10 times 2 is 20 oxygens, and I've got 8 oxygens right here. So on my product side, I've got 28 oxygens. That means that I would have to put 14 there. 14 times 2 would give me 28. Now that I've got this balanced, I'm going to do my stoichiometry part. And I'm going to rewrite this 10 here just to make it easier for us to see. Now, if you want to fill out this table and you want to do everything, that's fine. But we're only concerned about these two things right here. That's all we're concerned about. So I feel pretty confident that I've balanced my equation correctly. So I'm going to go ahead and just do everything with these two species, and I'm not going to worry about those two. First, I have to find the molar mass of this one and this one. So for C10H16, I'm going to come up here and get out of my way a little bit. I've got 10 carbons at 12 grams per mole. It gives me 120 grams per mole from my carbons. I've got 16 hydrogens times 1 gram per mole. That gives me 16 grams per mole from hydrogen. I add it together. So this one of these right here is going to weigh 136 grams per mole. So I'm going to write that down here, 136 grams per mole. Carbon dioxide, we've seen that one many a times, 44 grams per mole. Now, I have 1 mole of this giving me 10 moles of this. 1 mole of this gives me 10 moles of this. Now, if I wanted my answer in moles, then that would be fine, but I want my answer in grams, so I've got to use this as a conversion factor here. So remember, if you multiply grams per mole by a mole, I'm going to do this down here at the bottom, 136 grams per mole, and if I have 1 mole, that gives me 136 grams. So I'm going to write 136 grams here. Now over here, I've got 10 moles of carbon dioxide, which is 44 grams per mole, so 440 grams of carbon dioxide. Now, I have a whole lot more than 136 grams. So the way this equation is currently reading, it's currently reading 136 grams of this stuff burns and gives me 440 grams of carbon dioxide. But I have a whole lot more than that. I have 7.63 kilograms. So I don't have kilograms here, and if I want to do a ratio, they're going to have to be the same unit. So I could either say 0.136 kilograms, or I could just call this 630 grams. It's always easier to multiply than to divide. So I'm just going to multiply by 1,000, or move my decimal over 3 places, and I've got 7630 grams. The next thing I'm going to do is I'm going to get my ratio so that I know how to scale this up, and I've got 7,630 grams divided by my 136 grams. So if we were to put this in normal terms, this is like saying I have 136 grams of flour and I'm going to get 440 grams of cookies. Well, my recipe may call for this, but I want to use 7,630 grams of flour. How many cookies am I going to get? So I'm going to have to find what my scaling factor is. So I'm just going to take this number, divide it by this number. So I've got 7630 divided by 136, and my scaling factor is 56.1. So we're saying that we have 56.1 times as much as we're supposed to have for our recipe. That's all we're saying. So if I want to find out how many of these carbon dioxide cookies I'm going to make, I'm just going to multiply the grams by that ratio, and I get 24,685 grams of carbon dioxide. So nobody in their right mind says 24,685 grams of carbon dioxide. We normally just say 24.7 kilograms of carbon dioxide.